All right, a summary of what we've learned so far in 10.3. Given a plane curve defined by parametric equations, the first derivative is the derivative of y with respect to t divided by the derivative of x with respect to t. The second derivative is the derivative with respect to t of the first derivative divided by the derivative of x with respect to t. The denominators are the same both times. In class, we actually derived this formula and showed why it works. We could extend this idea to find the third derivative of our plane curve by saying the derivative with respect to t of the second derivative over dx dt and onward. A pretty big idea in this section, although you wouldn't know it if you read the section, is the idea about tangent lines in the context of plane curves. Consider the plane curve generated by this set of parametric equations. This is what the graph looks like. It's called a prolate cycloid, and it's no coincidence that it has the word cycloid as part of its name. Somehow or another, this path is formed by rotating some kind of a wheel in some way with a point on the wheel. I wonder what it means to be a prolate cycloid. Well, we know what this path looks like, but how can you generate that mechanically with wheels? Anyway, that's for a different discussion. For now, I would like you to notice that there is a point on this graph where there are two different tangent curves. Right at this point at 0, 2, we have a tangent line that's positively sloped and negatively sloped. Finding the equation of a tangent line in the past has been really easy, but how do you find the equation of a tangent line at a point 0, 2 when there's two different lines? So in this problem, we'll ask, find the equation of both tangent lines which pass through the point 0, 2 for this plane curve. Because the tangent line passes through the point 0, 2, we could say, let's solve for t when the x-coordinate is 0 and the y-coordinate is 2. Solving for t will be easier in this equation because there's only one term with t in it. There's two terms with t here, but we can't factor this t out, so let's solve this one for t. We really quickly see that it happens when t is positive or negative pi over 2. There are no other places on this graph where the y value is 2, so this must be the two distinct and unique t values for which we have our two distinct tangent lines, one that has a positive slope and one that has a negative slope. At this point, we could check to see if this satisfies the x equation, and you'll see that it's true. 2 times pi over 2 is pi. Sine of pi over 2 is 1. Pi minus pi times 1 is 0, so it works. This is our solution. These are the t values for which we'll have our two separate tangent lines. In both cases, the point the tangent line passes through is 0, 2. So now we just need the slope. So dy dx is dy dt over dx dt, and when t is negative pi over 2, we get negative pi over 2. And when t is positive pi over 2, we get positive pi over 2. And there are the equations of the two tangent lines which pass through the same point, or if you prefer, slope-intercept form. All right, so there's a part B under our focus on tangent lines in section 10.3. And while this example was done in the book, part B, they don't really discuss much in the book, but they ask a lot about it in the homework section. So definitely take notes right now as part of your homework. Open up your notes and take notes on part B if you haven't already started. The idea I'm alluding to is the idea of tangent lines which are horizontal with a slope of 0, and tangent lines which are vertical, whose slopes don't exist, they're undefined. How do these ideas play in with parametric equations? So when the tangent line is horizontal, it's either x prime or y prime that's equal to 0. What's happening? If a point was moving around the circle in either direction, as soon as we hit this point for an instant, just for an instant, it's not moving up or down at all. So that means dy dt would be equal to 0 just for that instant. Dx dt isn't equal to 0 because you'd still be moving horizontally at that point. But when you hit the maximum height, just for a brief instant, you're not moving up or down at all. Similarly, if a point was dragging around the circle and came to this point here, this tangent point, you're still moving up and down, but just for an instant, you're moving to the right, and then you stop for an instant, and then you're moving back left again as you come along over here. And just for an instant, the rate of change of your x value with respect to that t variable is 0. So when dy dt is equal to 0, we know we have a horizontal tangent. And when dx dt is equal to 0, we know that there will be a vertical tangent. Let's start with number 5. They ask for the first derivative, dy dx. That'll be dy dt divided by dx dt. And then they ask for the second derivative with respect to x. And that would be the derivative with respect to t of the first derivative divided by dx dt, which is 4, and this is 0. And then they ask us about the slope and concavity when t is 3. Well, the slope is 3/4, meaning it's a straight line, and the concavity is neither positive nor negative. Therefore, it's neither concave up nor concave down because, as we can tell, it's just a straight line. There is no curvature to this. It's a straight line because the slope is constant. All right, so we've got the first derivative, the second derivative is 0, the slope when t is 3 is 3/4, and is neither concave up nor concave down when t is 3. Well, the graph looks like this. The instructions are, and I quote, find the equations of the tangent lines at the point where the curve crosses itself. So clearly the curve crosses itself right here, and we will have two different tangent lines, this one and this one. Find their equations. Well, when they cross each other, the x-coordinate is 0 and the y-coordinate is 0, and they have to both be 0 at the same time. All right, well, the y value is 0 whenever the sine ratio is 0, which is the y-coordinate, so that's at 0 radians and pi radians and 2 pi and 3 pi. You can just tell looking at these functions, it's cyclic, so it's just going to keep going on forever. There's an infinite number of t values when y is 0. And when is x 0? X is 0 when sine of 2t is 0, so that's going to be a horizontal transformation. The angle still has to be 0 or pi, so if 2t was equal to 0, then t would be 0, and if the angle was pi, then t would be pi over 2, and if the angle was 2 pi, which made the sine ratio 0, then 2t would be 2 pi, so t would be pi, and that goes up by half pi's. Instead of going up by pi, it goes up by half a pi. All right, so we need two cases when they're both 0 at the same time. When t is 0, that'll work. That's a good one. And then maybe when t is pi. These are the first two instances when both the x-coordinate and the y-coordinate will be 0, which means it'll be passing through the origin, and we'll have our equation of the two tangent lines. So we've got our red one and our yellow one, and they both go through the point 0, 0. So using point slope form. And all we need after that is to know the slope right there. So we'll need to find dy dx for these parametric equations. dy dx is dy dt divided by dx dt. And when t is equal to 0, the slope is 3 times cosine of 0, which is 3, over 4 times cosine of 0, which is 4. And when t is equal to pi, 3 times cosine of pi is a negative 3, and 4 times cosine of 2 pi is 4. So y is equal to 3/4 x, and y is equal to negative 3/4 x. The equations of our two tangent lines that pass through the point where the graph crosses itself. All right, I think we'll do maybe one more example. Maybe we'll do 2 more examples. So number 29, x is 4 minus t, and y is t squared. And we're supposed to find any horizontal or vertical tangencies to this curve. So do you recall which of these will indicate a vertical tangent line and which will indicate a horizontal tangent line? For dx dt, x is not changing at all. When x is not changing at all, that's going to be a vertical tangent line. And for dy dt being equal to 0, that means the change in y with respect to t is 0. Y isn't changing at all. When is y not changing at all? Just for an instant on any horizontal tangent line. All right, so let's proceed. dx dt is never 0, therefore there are no vertical tangent lines. dy dt is equal to 0 when t is equal to 0, which is when x is 4 minus 0 and y is at 0 squared, or at the point 4, 0. And since y is not changing at all at that point, this is going to be a horizontal tangent line. All right, and now for our last example. For number 41, in problems of this type, we're supposed to determine the open intervals of t values for which this curve is either concave down or concave up. So clearly, we're going to need to know the second derivative. Let's start with the first derivative. The first derivative is dy dt over dx dt. We can combine those terms, and then we'll do the division of these rational expressions. All right, and there's the first derivative. And now let's do the second derivative. The second derivative of y with respect to x will be the derivative with respect to t of the first derivative all over dx dt once again. So dx dt is the same as it was last time, and the derivative with respect to t of the first derivative will require either the quotient rule or the product rule. I went with the quotient rule. Well, I've got the second derivative reduces down to 4t over 2t plus 1 cubed. So now to determine when is that positive and when is it negative. So when is the second derivative positive and when is it negative? How to figure that out algebraically with an expression like this? Well, here's one way, and then after this, on the next slide, I'm going to do this entire process a little bit different algebraically, and you can see which one you like better. Just know that sometimes it can be kind of difficult, like this case. All right, when is the second derivative positive and negative? It depends on whether the sign of the numerator and denominator is positive or negative. So we know that the numerator is negative when t is negative and positive when t is positive. What about the denominator? So the denominator's critical value is when this is 0, which is when t is negative a half. So the denominator sign will change, possibly, when t is negative a half. So if we check a value to the right of t equals negative a half, like 0, the denominator is positive. And when t is to the left of negative 1/2, for example, if t is negative 1, we'd have negative 2 plus 1, which is negative 1. Cubed is negative. So on this side of t equals negative 1/2, the denominator will be negative. So the instruction is, when is this plane curve concave up and concave down? So you might be tempted to say it's concave down when t is between negative 1/2 and 0, because that's when the numerator is negative, the denominator is positive. So the second derivative will be positive, or negative divided by positive, which is negative, concave down. Except that doesn't work because this plane curve doesn't exist when t is negative, because we have an expression, the natural log of t, that's only defined when t values are greater than 0. So we can actually ignore everything out here. We might have been tempted to say that the plane curve was concave up when t was less than negative 1/2, because the numerator divided by denominator was a negative divided by negative, which is positive. But again, we're not going to describe the plane curve as being concave up there, because it's not defined when t are negative values. T has to be bigger than 0. So when t is bigger than 0, is the second derivative positive. And when t is bigger than 0, the numerator divided by denominator will be positive. So the answer is when t is bigger than 0. The plane curve is concave up when t is bigger than 0. All right, in the next slide, I'm going to quickly show a slightly different way of doing the second derivative, a slightly different way algebraically. So we do the same thing. We do that the first derivative is dy dt over dx dt, and I'm just leaving the derivative of the natural log of t in this form instead of as a fraction. And then the second derivative will be the derivative of this entire thing divided by dx dt on the bottom again. And here I use the quotient rule, and again I'm leaving everything in exponential form. And then that simplifies all the way down to this expression, where the numerator is just 4 and the denominator is this. And basically the sign of the second derivative is dependent only on the denominator whenever the denominator is positive, and we get the same results as before. Exactly the same results, except remember the plane curve doesn't exist unless t is bigger than 0. So the answer again is only when t is bigger than 0, and that's when the second derivative is positive, so it's concave up for those values of t.